Today, on behalf of our EU consortium and in line with EU strategic partnership with mineral-rich country, I'm presenting one of the EU active project on lithium, which has the short name of the Li4Life. I'm sure all of you know better than me. In line with green energy transition, all those key green energy in terms of the electrification, wind tower, solar panel, they are mineral rich and also metal rich, which is a good news for mining industry in general. But we have challenges because most of these elements, they are not a base metal, and most of them is a byproduct and not easy to produce. And many countries, even in EU or UK, they had a little bit underestimating of the supply chain, and they have an ambition which is, from my humble belief, it's not that easy to fulfill. That's the reason EU has initiated many projects to localize that and accelerate that through the producing in EU or strategic partnership with mineral-rich countries. As you have seen many reports like European Energy Organization or World Bank, we need a significant amount of the increase in mineral production. Like in the case of the lithium, we need 600 times more lithium extraction in order to fulfill our target for 2050, or even in some countries in UK, 2032. And in the case of the copper, what we have extracted for last 5,000, we have to extract in next 25 years, which is a big, big ambition, and it's not easy to fulfill. And in terms of the electrification, when we're talking about the electrical car, unlike the many common belief, it's not that green and requires more metal. Like electrical car in average needs 6 times more metal than the conventional car. And these metal, as I mentioned, they are not like a normal metal. We are very good in producing that. So we have to address them, and mineral industry has a good opportunity to actually come and play the key role. The term critical raw material looks very new term, but practically mineral always have been a critical, because many of the human civilization era is the name of the mineral, from Stone Age to the Bronze Age, or even from the carbon or Space Age, all of them without mineral and metal, we cannot imagine we could actually fulfill that. But when we come into the modern use of this term, previously was privately and secretly dominated with the space science or military, and we wouldn't hear more about the critical raw material in public. But as I mentioned, in green energy transition, due to the intense need of the critical raw material, and right now we have more communication and discussion in the public domain in this aspect. And many countries like US already had initiated that secretly, but now is a common. And EU also, since after 2010, has initiated every second year a list of the metal or element as a critical. And this critical term also varies from one country to other country, what that critically means and how we can measure that. We have actually done a study looking at the EU list from 2011 up to 2023, how this list from 14 element changed for the 37 element, and what was the dictating factor. And we localized that for the case of the South Africa. I'm sure it might be very interesting. Each individual country try to list own critical raw material, not only from the local use, but also as a supplier. And that would be a key geopolitical shift playing the vital role in mineral supply chain. And definitely Mexico and the other countries also could play a vital role and trying to define them and not just randomly extract them, but in line with the global need and demand. In terms of the EU, as I mentioned, they started listing from 2011, and the latest list they had 2023, it was 34 elements. And previously, they a little bit underestimate the base metal like the copper, aluminum, because they assume we have enough of that, and they look at more other elements. But copper, aluminum, known as the cross-cutting element, they are really, really key, and we cannot have any electrification if we don't have secure supply of this element. That's the reason in the latest list of the EU, they name copper and nickel, not as a critical, but a strategic element, and they establish EU Raw Material Act, which is now a law, and they have an ambition in terms of the supply from primary and secondary resources. In UK, after Brexit, only matter, all the political party quickly and without any delay agreed. It was defining the critical raw material for country. And they came up with 18 critical raw material, a slightly different measurement, and they have accelerated, I believe, even more quick than the rest of the Europe. They minimize the administration. Many traditionally active area in Cornish, south of the UK, like Cornish Lithium, British Lithium, right now they are active. They merging with the France company Emirates and producing the lobby, and they also have a ministry level regular meeting, and our university and my team, we are actively involved. The idea is to accelerate UK leadership role, not only producing the mid and downstream role, but also collaborating with the mineral-rich countries. Example is the Pensana company. They will produce the rare earths in Africa, and the concentration will come to the almost like a less than hour from our university, and the final concentration of the rare earths, specifically for permanent magnet, will be produced in UK. And the project I'm just talking about, that is one of the EU projects specifically about the lithium and trying to get the lithium from non-spodumene and complex resources in Europe. This is the team for the kickoff meeting we had last year in Spain. And since we have Brexit in UK, in addition to the EU funding, we get the fund from UK Research and Innovation. Oh, sorry. And we have in total 13 project partner, 1 associate partner, and 40 different entity and the board member as listed here. And also we are official member of the Europe 2030 Battery Initiative, which is the leading initiative for battery industry and combining any relevant research from primary, secondary, raw material resources all the way to the final product in EU. Our idea in Li4Life is from sampling all the way to the final battery-grade lithium carbonate production, and different partners in different countries has a role. In UK, myself and my team, we are mainly towards the mid and downstream final production of the lithium carbonate using combination of the different techniques, which I will briefly explain today. And in terms of the sampling, we have already conducted sampling from different countries in Europe, from Serbia, Spain, Finland, and Czech Republic. 2 different samples from Czech Republic, 1 tailing and 1 primary sample. All samples go through the different processes, and the idea is we're using combination of the innovative technique from the mass waste rejection using smart sorting and in line with the full value extraction. Yes, lithium is the target, but we will look at the different high value component inside the sample we're getting, and all of them is the non-spodumene, so the project will be a new process and flowsheet development for these local resources. And in terms of the project, we will have like the TRL like 3, 4, 5 in the laboratory, and also later we have a pilot plan in Serbia, and we will perform the development process in the pilot scale in the facility in Bor in Serbia. And as I said, we have a different sampling already have been gathered, different partners working on that, and the starting TRL is the 5. The idea is use the combination of the physical separation, flotation, as well as the different green chemistry, specifically deep oxalic solvent and bioleaching, and combine the different lithium carbonate production route using the different LCA and techno-economical and environmental assessment. These are the objective have been established in this project, specifically targeting the increase in recovery, energy efficiency. These are the requirements for any EU project you have to fulfill. Sorry, I'm just putting front, it comes back. So in terms of our task in this project, which the UK, I'm representing UK, we are using the green chemistry to downstream production of the battery-grade lithium carbonate, and we're using electrochemistry and also bio-leaching approaches. In general, we have 3 main tasks. One is using green chemistry. We synthesize those reagents and in order to improve their selectivity and also from environmental perspective. And we also use the bioleaching combination of the indigenous bacteria we extracting from the soil and also the bacteria commercially we get from our partner. And also we have a state-of-the-art characterization technique. We have perhaps one of the well-equipped lab in UK. We use them from the atomic scale towards the molecular scale, both for reagent and the sample, in order to understand the rate limiting factor during the process. These are my team in university. Just I would like to acknowledge them. And these are the samples we have already gathered, and we received the sample after our partner in Germany or other country, they ground, crush, do the initial sampling. We get the after flotation or directly from primary resources, and then we apply different initial characterization from XRD, XRF, SCM, EDS, Raman, or ICP, and also FTRI. We use also simultaneous thermal analysis combined with the mass spectroscopy to try see if we're using the thermal processes, what happens during the process. These are our hydrometallurgical electrochemical processes. We are currently working on that and using different reagents from sulfuric acid, sodium carbonate directly, and also oxalic, citric, deep oxalic, and selective ionic liquid sample. And we're using pretreatment, mechanical chemical activation, curing, microwave, and digestion in order to compare which method can replace the high temperature currently lithium extraction process. And we also, for the PLS, we're using different purification technique from solvent extraction and also ionic liquid, and also we're using the direct carbon dioxide injection in system to produce the lithium carbonate, and we use also electrodialysis. All idea is to improve the efficiency and selectivity of the purifying the PLS and selectively precipitating or separating the lithium in the form of the lithium carbonate, which directly can be used in battery. And these are the couple of the results through our mechanical activation, and the idea is we try to weaken specifically for clay and silicate phases, then that would be in the favor of the leaching process, and we're hoping we will reduce the energy uses in the normal thermal processes. We also use the acid curing, and we have already obtained interesting result, which actually significantly help in order to avoid going close to the 1,000 degree. You can do it in the ambient or maximum up to 200 degree. These are our experimental setups, so I don't want to go and bother you too much. And we also have our mixed acid, and we believe combining this acid also increase the efficiency, and we also look at the different acid concentration. These are mainly trying to have an alternative method for current lithium extraction. We also have the acid digestion, and we're using different temperature and applying all our reagent. And the photos I'm showing here, these are my PhD students. Just it's my duty to acknowledge them and their great work. Digestion also, these are the setup we're using, and all digestion for the organic acid we go up to 100, and for sulfuric acid we go to 200, and follows with the water wash between ambient temperature and 50-degree temperature. These are also some of our results. And in terms of the thermal, since we do using the digestion, and in digestion system you have an input and output, you don't know what's happening in between, so we have applied the three in situ thermal processing, simultaneous thermal analysis combined with the mass spectroscopy. We have a thermal microscopy, can go up to 600, but the first one can go to the 1000, close to the 200 degree, and we also evaluating the XRD, but using the thermal XRD, and see in situ, see the changes in chemical as well as the mineralogical composition of the sample. And these are some of our studies. These are thin section, but not normal thin section, because we expose our thin section to the 600 degrees. So we have to use different binder for produce this thin section. Then we can use our thermal analysis. We also use some of the other technique, ultrasonic assisted leaching. In most of the cases, specifically for organic acid, we have seen a very interesting result. And as I said, one of the other aspects for us is knowing the fundamental aspect, specifically for reagent, we synthesizing, we're using viscosity, density, and these are the devices we use for viscosity. Yeah, and as I said, we have synthesized it up to 10 different dipocatic, and the idea is having acidic dipocatic solvent. For those might not be familiar with dipocatic solvent, these are known as the green reagent, has potential a little bit be more selective for some component, but we synthesizing them in the favor of our project, and then expose for different analysis, and those analyses dictate us which specific dipocatic solvent we have synthesized is suitable for our process. These are the list of the tests we do for each dipocatic solvent in terms of the FTRI, NMR, viscosity, electrical conductivity, and CV, and also EIS. These are some of our initial results, which we already narrowed down our dipocatic solvent for 3, which we apply in our leaching processes. In terms of the bioleaching, our idea is, since we collected different samples from different parts of Europe, we're trying to extract the indigenous bacteria from this sample, and we have a team jointly working with our life science group. And the idea is there any specific indigenous bacteria based on the mineralogy lives in that component? And so far, we have collected the DNA data, and we will sequence them and see. And one thing we have noticed, the composition of the metal is a dictating factor. If there's any poison metal in any component, then there is a zero chance the bacteria grow. So that would be a good, specifically for people trying to perform bioheap leaching or anything. Knowing the composition of the sample would be really great in order to improve the efficiency of the bioleaching. And these are our like the bio leaching and DNA studies, and those are more technical, so it's late. I don't want to tire you, and I'll just rather move on. And we are in the stage of the sending sample and sequencing our DNA, and at the same time also we're monitoring the in situ parameter, pH, EH, bacteria count, as well as the ICP to see is there any metal extraction during the process. These are our experimental plan for which stage we should select the sample for DNA analysis. Otherwise, we cannot compare or repeat the experimental later. And these are the ongoing work we have been, and we are in the stage of the next generation sequence of the data, and very soon we will receive the dominant bacteria in each 4 type of the Europe, lithium bearing mineral in Europe, and that would be also good. So I will leave you with my contact, and as I said, my responsibility on behalf of the EU project is establishing the partnership, and I would be more than happy for any collaboration through the ongoing EU project or future EU project, as well as directly with the UK funding bodies. So I thank you, and I will be happy if there's any comment or question you may have.